Good day, everyone. I am Jonathan Herbert, representing work done by Sterling Ramroach, myself, Jonathan Herbert, and Dr. Joshi on CUDA-ACCELERATED feature selection. So, first thing to do is identify what our problem is. So, feature selection is done to determine what are important features in respect to a response variable. And to do that, it removes noisy and irrelevant features. But for large data sets, this can actually be time-consuming, so we would like to accelerate this process using GPU acceleration. So our goal is to improve univariate feature selection using Pearson correlation. So univariate feature selection is where we select a single feature that we deem is the most important for our response variable. And we'd like to do it by parallelizing the process on CUDA-enabled Nvidia GPUs. And CUDA is a framework provided by Nvidia that allows us to do general purpose computing on GPUs in a scalable manner. So what we did in our process, so we use Pearson correlation as a measure of how important a feature is with respect to the response variable. What it is defined as the covariance of the feature with respect to the response over the variances. This gives us an indication of how useful a feature is with respect to variable. So to actually apply this to a data set, we have to use sample estimators for the covariance and variances. And the sample formula estimates are shown on the screen here as Rx, Y, and we use this sample estimator, the function to the sample estimator, to define a kernel which we will run on Nvidia GPU to actually perform the calculations. So how this actually works is, so what the CUDA framework allows us to do is define a kernel, which is essentially a function that we can request to do on the GPU to do work in parallel, in a similar way as the diagram shows, where we have blocks which also subdivide into threads on a grid, and this allows us the work to be broken up such that we can compute the Pearson correlation for each feature independently in our data set. So these are the results we obtained. So as you can see, the GPU outperforms the CPU in the process of calculating the Pearson correlation. As the number of features grow by factors of 10, you see that the CPU implementation is increasing essentially exponentially, while the GPU performance stays consistent. But one thing to note is currently for our univariate feature selection, a single feature is not actually useful because essentially you know which feature is the most relevant. So this is just for the purposes of benchmarking. And another thing to note is that actually for using a single feature, if we calculate time for a single feature, it will overall take more time because these times don't include the time to transfer the data from memory to the GPU's memory to GPU's memory. So it's only used as a benchmark to provide context for the higher dimensional data sets. So here's actually a graphical representation of the data that previously depicted, where you can see that the CPU implementation increases exponentially, whereas the GPU implementation remains consistent in its time it takes to complete our task. So the conclusions of our work is that we determined that using Pearson correlation conclude that since Pearson correlation is an effective method for univariate feature selection, and that we can actually do the calculations independently, we can use GPUs to significantly accelerate the process for large data sets with a datasets with a large number of features. So these are the references that we actually use to produce this work. Thank you for listening to our work, and now welcome questions on it.
Thank you, Akash. Thank you, Jonathan. Akash, you want to lead off, or would you like me to lead off here? All right, I'm not hearing from Akash. So, Jonathan, let me just lead off with a question. I'm not seeing any questions in the chat right now. So just to remind everybody, right, okay, here we got a question. Came in from Dr. Beichu. Can the approach be extended to bivariate selection?
I'm not sure bivariate. I'm assuming bivariate selection is where they're selecting two features instead of one. Okay, so in theory, yes, because effectively the process we did was computing the Pearson correlation with respect to the feature from each feature column to the response variable. So essentially that process would still be parallelized, and we can still just select the top two most relevant features. So yes, it should be able to be extended to bivariate selection.
Excellent. Is this something that's totally new, Jonathan, or have other people done this similar work before?
As far as I'm aware, this would be still most likely been done for accelerating essentially different feature selection methods for on GPUs.
And is this then a method that could have some commercial potential in terms of being able to transfer the technology, or who would be, would this be a software implementation or a hardware implementation, and who might be kind of the interested parties for actually taking up a technology like this, the algorithm that you've developed here?
As far as I'm aware, most likely be software implementation. I'm assuming, well, the relevant parts is useful for would be, I guess, machine learning and data science, machine learning experts and data scientists who are trying to reduce the number of data points to some subset that is most relevant for the data, because processing using all features in the machine learning algorithm would essentially be more costly than essentially limiting to some known useful few.
Do you have an application for the solution?
No, don't have one yet.
So what's the uniqueness of this presentation?
That I'm not sure entirely. That's a whole. I'm not sure. Sorry, again.
Yeah, no problem. I see we have a couple other questions. Can it be scaled linearly with multiple GPUs?
I'm not, because it's Sterling and Dr. Joshi were the CUDA experts. So I would assume yes. Assume if CUDA provides, scaled, yes, but I don't know if it'll be scaled linearly. I know it should be able to be scaled because I believe CUDA provides ability to use multiple GPUs, but I don't know about how it would scale.
And you're not too sure about the implementation, like if it could be used in the new RTX cores?
I'm not sure how CUDA handles it differently, but I'm assuming as long as it's CUDA-enabled GPU, it should be able to be run.
All right, I see a couple more questions here. Another one from Richard. Are you considering using any other measures of correlation or goodness of fit tests, such as standard error estimates?
I had not actually considered that. But I just decided to just use that. But I'm assuming, realistically, if it can be done independently, that it should be a viable method as long as it can be done independently to be scaled up, rather than it being required all the variables need. As long as each feature variable can be done independently, it should be able to be scaled up using the method.
Okay. All right. Jonathan, I realize that you are not the main person behind the paper, right? So I guess I could ask you, what is your input into this project, and how do you see yourself moving forward with the start that you all have?
Because my contribution, I did the reading for the background, so in the Pearson Correlation, so I did some of the background. So in the how it can be extended, this can be added as essentially a pre-processing step to some other machine learning process that, such as some other machine learning process that has to process a high amount of data, such as I'm sorry, I'm blanking.
You can take your time and answer. Right. I just want to get an idea of your skill set and where you come from, and how you are making a contribution toward this work. Right. So that's fine. However you answer.
Okay. Thanks very much for that, Jonathan. It's a very interesting presentation, and I think it certainly shows there's a lot of potential in that method, and it could be very beneficial to data scientists and to others in determining how to go about using the various processes and the computer architecture. So thank you.